Today's speaker is Mohan. He is a postdoc model working on solar stellar radio activities.
Yeah. So thanks, Yuta, for introducing, and thanks for inviting me. So I basically started as a solar astronomer, so basically in the radio wave band, and now I work across the cool star spectrum, starting from F to M dwarfs. So I'll briefly give I'll give an overview of various projects, and then so that interested folks can catch me, I'll be here the whole day, and we can discuss. Yeah. So okay, is okay. I hope now the full screen is up, right? This thing is not going, so yeah. Yeah. So I'll be talking about the various projects where we explored stellar activity across cool stars using sub-terahertz imaging tomography, basically millimeter to radio. And I'll start with the introduction. Yes. So as we know, the solar atmosphere is primarily made of three layers, starting from the photosphere, and it goes into the chromosphere and out into the corona. And as you move up, you can see that the temperature of these layers keep rising, as opposed to what we generally expect when you move away from a hot body. It should actually become cooler, right? But that's not what we see. And that's what we call, that's a result of this atmospheric activity, which is driven by these magnetic fields, which you can see the complexity of which actually increases when you go to upper chromosphere and out into the corona. And this is what we call the chromospheric and coronal heating problem, and the complex magnetic fields are the reason for that. So if you look at the general atmospheric profile of the sun and the stars, so here the G2V is what our sun is. And starting from photosphere, you initially see a temperature dip. But then you see in the upper chromosphere that there is a steady heating, which actually gives that huge thermal gradient, and out it keeps increasing into the corona. And interestingly, this picture is similar even if you look across the cool stars. So the other example is from an M2V star. It's a much cooler star than the sun. And there also you see an initial dip starting from the photosphere, but then a sudden rise, and as a result of this magnetic activity. So that's interesting that we have a similar picture across the cool stars and how the activity presents itself in the atmosphere. And what drives all these activities, basically the convective motions down in the convection zone of these stars. And that basically twists and turns the magnetic fields, which are in the photosphere, like you see here. So what you see here is a magnetogram movie where the opposite polarity magnetic fields are shown in the red and the white. And by virtue of these turbulent convective motions, you have these active centers being constantly churned and twisted around, and which in turn builds the stress and strain in these magnetic fields, which is stored as excess magnetic free energy, which has to be released for equilibrium. Series of events which we call reconnections, where you have these magnetic fields with highly strained magnetic fields, and the energy release happens when you have the strained magnetic fields being reorganized into new fields, which we call as reconnections. And reconnections basically accelerate the electrons and particles in that local area, and reconnections happen across the atmosphere at various scales, as we know it in the sun, starting from a few kilometers out to sometimes across 10 kilometers wide, creating all these X-ray jets, the spicules, what we call these minor ever happening small processes, and so on. So we have a general picture that these strong dynamic magnetic fields are the reason for all this activity and heating across these atmospheric layers. Now, sometimes this can happen across an entire arcade of magnetic field structures. Like in this case, there is a low-lying loop structure which is becoming unstable, and it is pushing the overlying entire arcade. And in those cases, sometimes reconnection happens across a much wider scale, creating what we call the coronal mass ejections, or the CMEs, like you see in this movie. So just to give you a scale of the CME, this is actually a data-driven model, basically the Enlil model, where you see a CME event happening from the sun, and it actually evolves into the interplanetary medium. And here is our tiny Earth, and you can see the scale is much larger than the sun itself. So this is kind of the plasma processes that we have to worry about as planetary beings, which are more closer to the sun. And similar events can also be expected by virtue of the same kind of activity in other stars too. And yeah. Yeah, so now combining all these different flaring activities and all these decades of observations we have in the sun, we culminate everything into what we call something like a standard flare model. Okay, so the standard flare model basically encapsulates the main funda of how these reconnections drive these activities. So it starts with the strained magnetic fields undergoing a reconnection event, which creates these particle jets, basically high energy electron and ion jets, basically the electron jets, which is bidirectional from the reconnection site. It moves upward and downward into the corona, and it hits the sublying layers and also the overlying layers. Sometimes it is so strong that it can actually push the newly formed magnetic field structures, which we call plasmoids, and push it out into the interplanetary medium, and then you get the CME. Okay, so the basic picture is that it starts with a reconnection, right? So it starts with generating these electron beams, the energetic electron beams, which is an impulsive process. So you should get an impulsive response first, which is usually seen in hard X-rays and radios. Okay, and after that, you have this gradual heating of the magnetic field structures, which is often seen as soft X-ray emission and emission across spectral lines, which span the different regions of the atmosphere. For example, H alpha, which is in the chromosphere, and so on. So this is the general picture that we have. Now, the thing is that all what I talked about is about the sun and what we know about the sun. And then I call this a standard flare model, right? But is sun a standard star? Isn't it too optimistic, right? So do we have to check it first across the entire stellar spectrum and ensure that this is really a standard flare model? Yeah. So that's what we do. So there has been various signatures of this standard flare model, which has been seen in different types of stellar flares. For example, here, this is the impulsive phase from the accelerated electron beams that I talked about. And then there is this nice soft X-ray spectrum. So this is from the sun during a typical flare. And this observation is from an M dwarf. So we do see cases where we have this kind of impulsive and following gradual phase emissions. But at the same time, we should, when we look at the entire stellar spectrum, this is not always true. So there has been cases where this kind of signatures have not been seen also. So when you look at the spectrum of stars and ask the question that how stellar activity varies across the main sequence, for that, this plot is a good starter. So what we have on the Y is basically the rotation period of the star. So the faster the rotation period, the high angular momentum it has in the surface, and also more violent dynamos can be triggered because you have a very fastly rotating like convection zone as well, right? So when you look at the rotation period versus the surface temperature of the star, or what we call basically the color B minus V is a proxy to surface temperature, as you can see here. Like so the higher the color, it actually moves from F to M dwarfs, which basically spans like 7,500 to 2,500 Kelvin. So you can think of this as like going to more cooler and cooler stars. Okay. So we can see that in this plane, basically the stars form two different populations. One is this slow rotating stars, and one is this very low period or very fast rotating stars. Okay. So we now know that these slow rotating stars, the stars basically start out as fast rotating stars, which are low periodicity, because when they are formed, they have high energy, high angular momentum, and slowly they migrate into this other population, which is slow rotating and less active stars. And to give you a picture of this, so here what we have is the age in one axis, the age of the star, what we can infer in many of these stellar clusters. And here is the fraction of stars in these different populations or different branches. So we'll focus on this one. This is the fraction of stars basically in the I branch. Okay, the slow rotating branch. And you can see that when you move in age, the fraction in that branch actually increases. And this is basically the fraction of stars in the C and the interim branch. And that basically falls down. So the stars basically start out as fast rotating and more energetic ones, which are more active. And then slowly they move as they age into like giga-year ranges into these less active ones. So as a result, their atmospheric structure should also change. Their angular momentum and many other factors are actually changing, and their activity type also should change. So to know this in a better way, we should basically trace all these stars in this rotation period T effective plane and understand how the activity works, right? So now, why do we generally care about this? So we have to care about stellar activity and solar activity because we are planetary beings, first of all. And like I showed, CME can anytime hit us. So, and the other important question we are after is also that, is it possible to have life elsewhere, right? So stellar activity is the major villain to all this. So in doing that, we take two different approaches. One is basically that given that Sun-Earth system is the only known system right now for us where there is life, we have to make benchmark models of the Sun and the Earth system and make Sun as a star models which can be scaled to other stars, right? And get a sense for like where they sit in this grand frame. And the other thing is that, like I already said, activity can be different in different stars. And like the young ones are more active and so on. So we need to also understand the entire F2M branch of stars and understand how the activity in them is in an independent way. And then try to find connections with our own system. So now why again F2M branch? So if you just ask the question of like, what is the probability of finding an Earth-like exoplanet in an habitable zone? And if you plot the stars in the x-axis and plot the probability in the y-axis, you can see that when you go to more and more like less massive stars or the cooler stars, the probability actually increases. Okay. So that's why we are more interested in the F2M branch. Yeah. So now to do that, we like I already mentioned, the atmosphere is actually multi-layered, right? So we need to have a tomographic exploration strategy, which covers across the chromosphere to corona to basically understand how this thing actually evolves. The activity actually starts in the chromosphere and evolves across. So the rest of the talk, I'll try to convince you that basically the Sub-Terahertz band is a very good band to do this kind of a tomographic exploration, something like a radar kind of a thing across the atmospheres. So starting with coronal tomography with meter band emission. So why meter wave band? Yeah, so when you ask the question like, okay, given the coronal parameters like density, magnetic field, and so on, so you can basically define the coronal plasma based on these fundamental physical fields, right? And you can ask the question that, okay, what are these different plasma modes in these coronal layers? So the basic plasma modes are basically the plasma frequency, which is a root of Ne, and the gyro frequency, which is basically a function of magnetic field, right? And if you plot that across heliospheric distance or like distance in the corona at different heights, you can see that all that basically falls in a few hundred megahertz, and that's the radio band. Okay, so because of this reason, so various kinds of plasma instabilities like shocks, flares, etc., can accelerate these electron beams and generate instabilities in the corona, and they will produce wave and wave particle interactions at these fundamental modes, producing resonant emissions at these modes, right? Because they are the fundamental modes of your system. And as a result, if you observe the star or the sun in these wavebands, you should be able to see coherent radio bursts, which is basically from free electron maser kind of an emission mechanism, because it's the fundamental modes of the plasma in the system. Okay, and since these fundamental modes actually change with distance, right? Because magnetic field evolves with distance, you move distance away from the corona, or like the density also varies as a gradient. So you can basically make images of these stars or the sun across different frequencies and basically trace the evolution of these instabilities or shocks across the corona, right? So they are direct proxies of propagating stuff across corona. And that's what you want when you want to study space weather. Yeah, so two of the main emission mechanisms are the electron cyclotron maser mechanism. And this usually happens when the flare site or the instability site, you have a condition where the plasma frequency to gyro frequency mode is less than 3. Basically, it is magnetically dominated plasma. And the gyro frequencies can be thought of as the frequency of the electron gyration, basically, in these magnetic fields. And the plasma emission is the other mode of coherent emission mechanism, which usually happens when at the flare site you have the plasma frequency much higher than the gyro frequency. So the gyro modes are basically suppressed and the plasma wave modes are dominant. So there you will get emission at the harmonics of the plasma frequency. Okay, so how will you distinguish these two emissions? It's basically based on the polarization of your observed radio waves. So the radio emission is usually nearly 100% polarized when you have an ECME mechanism. And in the plasma mechanism, it doesn't usually go that high. Okay, it's usually around like 70–75%. That's basically because in these flare sites, you have a lot of density turbulence in the medium, which can depolarize your emission, because the emission is fundamentally formed at the plasma frequency, right? So if that is keeping on changing because of your turbulence, then you have depolarization. Yeah, and the other interesting thing is that since this is some sort of an electron maser emission, it has to be beamed. It cannot be 4π, right? Like your simple laser, right? So when you are looking directly at it, you will get the highest intensity, and when it is wide, when your line of sight is wide, you should basically not see much of it. So that's the thing. So the coherent emission can be inherently beamed. And why would you care about beaming much? It's basically because of this. So here what you are seeing is a solar flare event. And this is the radio dynamic spectrum, where you are seeing the intensity of the radio waves as a function of frequency and time, right? And you can see here that there is this nice drifting radio burst, which is a sign of something which is actually propagating out into the interplanetary space. And here you see something which is band limited and which is just existing for some few hours, right? And this is the same event observed from stereo A and stereo B. These two are observed by stereo spacecraft. The good thing about stereo spacecraft is that they give you multi-vantage point observation of the same flare. Okay, so when one is observing it from the right, the other would be from the left. So like you see here, the flare was actually on disk in stereo A, and there you see this nice drifting burst and this propagation of electron beam across. But when you are looking at stereo B vantage point, where it is more towards the edge, so it's not directed towards you, you don't see both the bursts. You see? So this is very important also when you look at stars, right? So there is a lot of hype about like the missing radio bursts and so on, but you could be missing it just because you're not looking at the right line of sight. But you would finally end up saying that, oh, yeah, the standard flare model is not right? But that's not the case. So you have to worry about this beaming in this. So yeah. Now coming to the different types of radio bursts, which you expect from the standard flare model. So like I introduced you to the standard flare model, this is the same thing. So you have these reconnections and the electron beams which are moving down and kind of depositing their energy in these post-flare loop structures or post-flare arcades. And these electron beams usually give you the type 4 radio bursts. Okay, so the type 4 radio bursts are these things which you see in the dynamic spectrum as band limited, existing only for a few frequency ranges and for around a hour time scale. So now why are they band limited? You can understand it from the plasma emission framework, because the emission frequencies are directly correlated with heights, right? Heights where the plasma frequency is in that range. So since your arcade exists only for some height, your emission should exist only for a band. So these are direct evidences for post-eruption arcade electron beam activity. And the other thing is this type 2 radio burst, which is slowly drifting at a pace across your frequency spectrum. And now why are they drifting? Because they are associated with the CME shock propagation. So CME shocks travel at around like 1000 kilometers per second and higher. And these are the electrons which are accelerated at the shock and which are emitting the radiation. So as the CME propagates, your burst frequency also drifts in your time domain. So that's what you see here. Okay.
We have a type 1.
Yeah, but that's yeah, that's even without any of this. Yes. So yeah, and the other one is the type 3, which is usually connected with these flare reconnection site associated open magnetic field structures. So that's like a free highway for the electron beams. Nothing is blocking them. So they drift very fast across these open magnetic field lines, and they form the SEPs, the solar energetic particles, right? And that, because they have this freeway, so they drift very fast because they are usually very, very fast, like c/3 speeds often, and they drift very fast. And that's what you call the type 3. Now, these three are very fundamental to the standard flare model, as you can clearly see that without a post-eruption arcade, where is the, where is the model itself, right? Yeah. So now when you take these different burst types, and then ask the question that, okay, I take all the solar energetic particle events and ask the question, which type of radio bursts are statistically more connected to like very fast CMEs, very active events, which are the major drivers of the space weather and, geoeffectiveness. So in the x-axis, what you have is the different radio bands starting from decimeter to kilometer. And the different line plots are for different types of radio bursts, and like type 3, type 2, and type 4. And here in the y-axis, what you have is the median flare class associated with these bursts. Okay. And you can see that the type 4s are like systematically associated with the most fastest CMEs and the most strongest flare types. Okay. So these are very important bursts which are associated with some of the strongest SCPs and the strongest CMEs and the strongest flares, and especially in the decameter heterometer band. And that band basically in frequency range is 1 to 20 megahertz. Okay. So what we try to do is like, we try to study these type DH, the decametric heterometric DH type 4 radio bursts. And this can be studied only from space, because this is in the 1 to 14 megahertz band, which doesn't penetrate the Earth's atmosphere. So you have to observe it only from the space. And interestingly, we also have these stereo spacecrafts, like I introduced, they observe these bursts from different vantage points, giving us a good view of like what type of events give you a very good type 4, why you might be missing some of them, and so on. Right. So we made a comprehensive catalog of like decades of these observations since the beginning of the wind mission in 1996 and the stereo mission in 2006 until now. And we have this catalog now, and we can now, we also have like 77 events with multi-vantage point observations, at least from 2 different satellites. And we asked the question like, okay, what kind of CMEs are they generally associated with? They are like, we expected, they are like associated with CMEs which are more than 1200 kilometers per second, and 80% of the time with halo CMEs. So both solar and stellar people should be very interested in these kind of bursts, because they are associated with some of the most violent phenomena out there. And now we went on to ask the question of like emission beaming, how emission beaming, inherent beaming in this emission actually affect your detectability of these bursts. So what you see here in the x-axis are the different events, like type 4 events, which were recorded by at least 2 satellites from 2 different vantage points. And the y-axis is basically the line of sight, or the source location as seen in the satellite, which is basically your line of sight to your post-eruption arcade. And we see that these colored dots are the best observed events, by which I mean the event was the most intense and which lasted for more time and more frequency extent. So you observed the most grandest of the type 4 among the different recorded ones in some sense. So all the time, this best viewed event, you can see that clearly is bounded within plus minus 50-degree line of sight, plus minus 60-degree line of sight. Okay. And whenever you had a spacecraft observing it, let's say, like even outside of this, for example, here near the limb, you just barely detect it, or sometimes like here, not even detect it. So whenever there is a satellite which was observing within plus minus 60, you get the best view of the event. So that could be the inherent beaming angle of these emissions. So that's what we found. And now we try to apply it to the stellar realm. Okay, so in the stellar realm, what is the problem? What is the big issue here? So we have a lot of active stars out there which even produce super Carrington flares at a very high rates. So super Carrington flares, like Carrington flare is the strongest ever recorded flare on the sun, and it happened only once till our recorded history. And these guys produce them like every other day. So they are like super strong. I mean, but the curious thing is that they didn't show any of the standard flare model expected radio bursts ever till now. So by which I mean the type 2, type 3, and the type 4, right? So this has been a big problem why like people have been searching for decades, like where are they, right? So, and there are now like some theories of how you can probably block them. So for example, type 2s, like I said, they need shock acceleration and the CME should accelerate it. But what if the outflow didn't even cause a shock, right? So these stars, for example, their magnetic structure looks like this. So they have a predominant dipolar magnetic field shield actually in them. Okay, so unlike the solar magnetic field structure, they have a dominant dipolar magnetic field shielding. So the idea is that even if the flares are so strong and they might be producing outflows, but the alphane barrier is so high because of the high magnetic fields out there that they don't cross that barrier and form the shock. Okay, so yeah, fine. So you can block type 2. Now type 3s. So again, because they have a strong magnetic field shielding and dipolar fields, you don't have enough open field line channels. So then you don't have the free highway for the electron beams. Yes, now type 3s. But type 4s, they are post-eruption arcades, right? So post-eruption arcades, there is no way of blocking them. If there is a strong flare, even if it is a confined flare, there should be electron beams in these post-eruption arcades, and you should be able to see them. So that has been a big problem. So we took this interesting star as our study case, which is Eddie Leo, which is a very young star. Like you can see, its rotation period is like 2 days. That's like 1/10 of the solar rotation. I mean, that's super fast. And it's like 250 mega year old, very young. And we also, there has been like Zeeman Doppler imaging studies of the star, which actually showed its magnetic field structure and the, dipolar field strength and so on. So we have a sense for what the magnetic field structure is roughly from the Zeeman Doppler imaging studies. And the recent studies have been showing that the star is actually going through probably an activity cycle because its dipolar shielding has been weakening down. So it used to be like 90% predominantly dipolar, but since 2000, around 2019, it has been dropping to 70% and so on. And being a solar physics, that's good news. We know that it's a magnetic activity cycle, right? So probably there is more active regions on the star. And another thing is that from the Zeeman Doppler imaging study, we know that the star along our line of sight is its south pole is along our line of sight. So it's oriented around roughly like 20 degree along your line of sight. And in these active stars, unlike the sun, the higher latitudes hold most of the active regions. So that means you have a good line of sight towards the active region belt. And since you are already looking at this top region, and when the magnetic field shielding becomes weak, you can have these interchangeary connection possibilities also with the polar field, right? So we thought that this could be a good candidate and we targeted it. And yes, so we got the first type 4 radio burst in a non-solar type star. Yes, so this is basically for comparison. So here what you have is one of the type like CME associated radio burst on the sun. This was a dynamic spectrum from the sun during a halo CME, which was moving at 2000 kilometer per second, very fast halo CME. And you can see these type 3s and a weak type 2, and then there's some sort of a type 4. And this is the AD Leo dynamic spectrum, which we saw, where you see this long duration type 3 like radio burst signatures and this band limited type 4s. Yeah, but there is a significant difference between the burst emission mechanism. So we in the sun, we usually have plasma emission mechanism for these bursts because the solar magnetic field is not that strong when you move like 1.5 solar radius and so on compared to the plasma frequency levels. The gyro modes are like suppressed. But these stars, we know that they are like 10 to 100 times more stronger magnetic fields. Okay. And so also we find that the emission mechanism as opposed to the sun is actually via an ECME mechanism. How do we know that? Because these emissions are nearly 100% polarized. Okay. So in the sun, at max, we see something like 30%, 50%, as opposed to this, which has like 100%. So now from the theory, which I initially mentioned, we can expect that this should be formed at a region in the corona where plasma frequency to gyro frequency ratio should be less than 3 because it's an ECME mode emission. And since we have the Zeeman Doppler imaging maps, we can kind of get the photospheric magnetic fields, and we can extrapolate it by using some profile. So we chose 2 profiles. One is a solar-like active region profile. And using that, you get the magnetic field in the corona. You can basically then get nu B easily, right? It's just a function of that. And the other model which we tried is a simple multipole expansion model, respecting the ZDI magnetic field results. Okay, and we made and we also had like from X-ray observations from previous, we can get the coronal density in the pre-flare phase. So you can also use that density to get a plasma frequency profile of your corona, right? So now combining them, we can basically have like the nu B of R and the nu P of R, and then ask the question like, which of these 2 magnetic field models basically can create a condition in the corona where nu P to nu B ratio is less than 3. And we did that, and we find that none of the solar-like average models can do that. So these guys' active regions are like pretty different beasts. So which was interesting, and that's about the corona. And now I'll give you an introduction into the chromospheric domain. Now we talked a lot about the corona and everything, but starts in the chromosphere, right? It's the upper chromosphere and the lower chromosphere which actually starts this magnetic activity and so on. So we need to understand the seed before getting the full picture. So there, I introduce you to this millimeter emission domain, which is basically like 30 to 1000 gigahertz band. Why is this interesting? So this is basically a plot made based on the 3D atmospheric model of the sun. Okay. And what we basically did is like we asked a question of like, what is the emission contribution functions for these different millimeter frequencies, starting from 30 to 1000. And if you plot these contribution functions, you can see that these contribution functions basically peak at different heights in the chromosphere. Okay. So, and the emission is also primarily thermal. It is basically the thermal Bremsstrahlung from the electrons. So you can basically read off the temperatures from the millimeter fluxes. And they actually track the different chromospheric layers. So thus the millimeter emission spectroscopy can give you a sense for the evolving structures across the chromosphere, and their temperatures can be directly read off. And the same exercise was done for the AD Leo, the M dwarf. And we see that the same thing can be applied where different millimeter frequencies can actually form at different heights in the chromosphere, whereby you can do a direct tomographic exploration. Okay, so we exploited this thing, this unique character of millimeter waveband, and we took all the stars which are observed in ALMA so far. ALMA is a very sensitive millimeter interferometer in Chile. And we found around 13 main sequence stars, which ALMA observed over the course of the time it has been observing. And they span from A dwarfs till K dwarfs. Okay. So here is a snippet of some stars, so which we had in our sample. So the plot, in the plot, you are seeing basically the brightness temperature derived from the millimeter fluxes. And like I mentioned, this would be directly correlated to the electron temperatures in the different chromospheric heights, right? And you can see the dotted line is basically a Phoenix atmospheric model where the stars photospheric emission is modeled. So it's purely photosphere only emission. And that would predict this kind of a spectrum for each star. So every star has that dotted line. And here you see that the A dwarf very well sits in that dotted line. And this is here in the x-axis is the frequencies, and towards the left, you have the decreasing frequencies, which means increasing heights in the chromosphere. Okay, so as you move away and away from the chromospheric height, so the A dwarf actually the temperature drops, and that's what you would expect when the star doesn't have an active atmosphere, right? And that's what you would expect in an A dwarf. They don't have an active atmosphere if it is around A1, A2. But what happens when you go to F and M and K? So this is what happens. So here lies the photosphere and the chromosphere is somewhere else, right? So it's doing what it's doing. So we see that there is a systematic rise in the temperature. And so what we did is like we can then characterize this temperature gradient using millimeter spectral indices, right? So that's what we did using this parameter called alpha mm, which characterizes the millimeter thermal gradients in the active atmospheres of the stars across the main sequence. So here we have sun for comparison. It's a sun as a star disk averaged fluxes. And the lines black and red is basically from a solar chromospheric model, the well-known FAL-C, FAL-A models. So you see the millimeter points are lying exactly in what you expect from a chromospheric thermal emission. So that again reinforces the argument that this is actually chromospheric thermal emission. Okay. So what do we find across the main sequence? Yeah, that was interesting for us. So all these black, like dark markers. So sorry, the big markers are basically for sun-like stars, which is basically the I branch greater than 1 giga-year-old stars. So we had a lot of them in the sample. So we sort of modeled their alpha mm or the thermal gradient in the chromosphere across the main sequence or across the T effective, the effective surface temperature. And what you see is like these are the A dwarfs, and they have like negative alpha mm, which is basically that dipping thing. So there is no active atmosphere. So above 0 is where all the activity should start, right? Where it starts heating up. So we find that you can get a nice trend with alpha mm and T effective, and somewhere around 8000 Kelvin is where all this activity which we are worrying about is basically starting in the main sequence. Yeah. So we also find that there are interesting trends. You can find like simple correlation curves with other important stellar parameters like rotation period and so on, which is where the activity basically bifurcates into the two branches, right? Yeah. So then we went ahead and like, okay, all this was for the sun-like stars, right? So what about our AD Leo, which is a completely non-solar type C branch star? How does its chromosphere behave, right? So this is a data which we took from NOEMA telescope, which is in French Alps, and we observed around like 85 to 100 gigahertz, and these points are basically from the millimeter observations. And the spectrum which you see is basically a theoretical spectrum, which is a data constrained model based on Phoenix code. So what we did is like we took the photosphere and we put a chromosphere on top of it, which is consistent with the UV emission. Chromosphere emits in UV. It's a prolific UV emitter. So all the UV lines and all the emission beyond the photospheric V band, which is observed for the star, was used, and then a well-constrained chromosphere was built. Okay, and we extended the chromospheric thermal emission to millimeter band to see whether how the points fit in. And what you see here is basically the departures from the model. Okay, and you see the model very well explains the UV emission, but when it comes to millimeter, it's actually deviating. This is completely not expected, right? So I already showed you that for the sun and stars like that, we have a very nice chromospheric model there, but here we don't know. So when you look at the alpha mm T effective plane once again, all the sun-like greater than 1 giga-year-old stars lie here in this nice blue line, but this guy is like completely off. I mean, doesn't care. So yeah, so we think that this could be some sort of persistent non-thermal emission contribution, which is adding on top of, the thermal expected contribution. But unfortunately, even though we applied for UV observation simultaneously and so on, which would have helped us to constrain that in real time, right? When you have simultaneous data, the simultaneous other wave band data we didn't get them. yeah, it was, the observations failed basically. So we are left with just this, but yeah, this is where we are. Yes, so yeah, then I also wanted to introduce you to the new telescopes and exciting stuff which is coming in the sub-terahertz band. And we have the square kilometer array which is coming up, which is going to extend our capability of imaging from 50 megahertz to 15 gigahertz. Like that covers a very wide band. And also with ALMA and NOEMA added on top, we'll have like 30 gigahertz to 1000 gigahertz and near seamless coverage where we can do this kind of tomographic exploration across chromosphere to corona. And these instruments are also good for solar. For example, this is from a SKA precursor, which is called the Murchison Wide Field Array Telescope, which has been operating in Australia. And during my PhD, I has been extensively involved in doing this solar stuff with these, and even now. So this is an example to just show you the power of these new imaging techniques. So before the MW era or the SKA era, we didn't have this capability of imaging the solar surface at even a second cadence. So now we have boiled it down to like 0.1 seconds. So we can basically image the sun at 0.1 seconds across this wide band from something around 80 to 300 megahertz, covering around 1.1 solar radii to 1.5 solar radii. And look at the morphology variations of active regions across the solar disk in this wide height scale. So here, this is actually a snapshot of one time slice and across different frequencies. Covering 1.1 solar radii to 1.4 solar radii, and these bright regions are the active regions on the sun. And interestingly, nothing is happening on the sun during this time. There is no X-ray activity at all. So, and Utah, this is basically the type 1 noise storms, which he was mentioning. Yeah, so the type 1 noise storms are basically a result of persistent activity in the active regions in the radio domain, which often does not have a clear X-ray correspondence. This is because there is always these microflares and nanoflare kind of things which are happening, always reconnections happening at some scale. So we actually made, we can now with this kind of imaging explore this at 0.1 seconds, how these things vary and how these things are transported across the corona, and make dynamic spectrum specifically for these different regions. And that's what you see here. And you can see this nice like frequency time blobs which are there, which is existing only for like a few seconds. Okay, and these are signatures of electron beams which are constantly being generated. Yeah. And here, this is actually how this is actually at one frequency, meaning one atmospheric height layer. And what you're seeing is like how the active region morphology changes every second. These are all just 1 second cadence images. So you can see like the same active region very dramatically changes. This is because these energetic electron beams and the size of these accelerations can, their dynamical scales, the electron beam dynamical scales are so fast, right? Yeah. So this is again just for comparison. So this is where the SKA would be. This is the angular resolution versus the frequency of operation. Just for comparison, these are some of the best telescopes out there. So the HST, so SKA, once it comes online, fully operational, it should hit the levels of HST angular resolution. That's the aim. And ALMA already hits something like KEK. Okay. So in nearly touching like sub-milliards second kind of scales. Yeah. So yes, so these are the main takeaways. So with these improved instruments across like the sub-terahertz band, we can now probe solar stellar activity across the chromosphere and out into the corona and how they evolve. And we report the first discovery of solar like radio burst associated, and which is like the cornerstone of standard Fourier model for the first time in a non-solar type star. And yeah, with millimeter imaging, I already showed you how and where the activity actually evolves, probably in the cool main sequence. And we are still observing different types of stars to understand how the activity is different, how the chromospheric response is different during the quiescence and the activity as opposed to solar-like stars. Yes, and thank you. Mhm.
So, actually, I have two, but so why is it that, we haven't detected any type 4 radio emission before in these stars if, if it shouldn't be blocked? It should, like, why isn't it taken until now? Is it like resolution or something?
It's not resolution. I think it's also about, like I said, which stars you choose is very important. If you look at these things and which stars and what phase of activity they are, all these matter. So previously it was like more like a blind eye search, I would say. Like you take all the active stars in the neighborhood, just stare 64 hours, 65 hours. But like I mentioned, if you are not looking at the active region in the right way, then the line of sight is something which people probably didn't take much note of. That could be one. And the other one is probably like, yeah, and then you got to be lucky that something is not blocking you along the line of sight. That's also one thing. So yeah, we need more sample. I would still put, like, to see why we missed.
Actually, I have something about the type 4.
Uh-huh.
You explained them again. I didn't understand.
Sorry. Yeah, so yes. So they are basically these electron beams which are like accelerated at these reconnection sites and then pumped down into these, newly formed flare loop arcades.
With the standard flare model. The standard flare model, you have the reconnection and
Yes.
the primary electrons that impact
Yes.
the dense atmosphere,
Yes.
which evaporates. That is what forms your post-flare loop. That hot plasma that slowly cools down.
Yes.
Once
So
you don't have electrons anymore, so that's that.
So if you have the electron beams because of the constant reconnection which is happening. So for example, like in the last plot, I was showing that snippet of the sun where you see when there is no flare at all, you still have persistent reconnections. So whenever you have this electron beam acceleration which is there, right, and the electron beams, so the radio emission primarily forms when these electron beams impinge into the ambient corona, it generates something like a two-stream instability, right? It's two-stream instability. Yeah. So that's when this generates the Langmuir waves, and which is later on converted into radio emission. So whenever you have electron beams which are generated at reconnection sites, you have them.
So you need to have a dense corona to
No, you don't need density like that. No, but after the flare, you expect these electron beams to fill up in your magnetic field structures, right? So there is a reconnection. So that's why you see there is this type 2s, they are almost always associated with major solar flares because you have these open field line exits and also, and that's the same electron beams which move down. And when they are trapped in these loops and, and they are still active, yeah, you get the type 4s. So that's why the type 4s exist for like around a few hours. Yeah.
So even though like this, the reconnection that
Mhm.
produces this emission is pretty ubiquitous, it's also associated with like the strongest or most rough.
Yes. Yeah, not always, even in the sun, you see a type 4. So that's also one thing. So they are pretty rare. Yeah.
Yes, on the next slide, you mentioned that, sorry, it wasn't the next slide. When we're talking about why we don't see type 2, type 3, type 4s in N4. At some point you said about maybe N4s don't have open field lines. Whereas, what's the difference between, say, an N4 and a J and that you have the open field lines in G-star and
Oh, okay. So why I made that comment is basically because of this strong dipolar magnetic field structure which the M-dwarfs have. So if you look at the Zeeman Doppler imaging results, most of them for these active stars, nearly 90% of it is predominantly dipolar. Okay, but that's not the case for probably a G-dwarf. So they don't have that strong magnetic, their dynamos are like pretty strong that they create this strong shielding thing. So there is every loop or every magnetic line you can think of it is coming back, right? And there is always some dense plasma in these visibly locked. So yeah,
Is it?
but yeah,
Is it like, it's just, difference in field strength?
yes, it's the difference in the field strength. Yes.
So I just want to like refresh myself from the beginning. Like, we're assuming like the chromospheric and coronal heating problem is possible, if not probable, for like many cool stars, or if not all.
Like all of them have the
Okay.
chromospheric
So
heating.
then I was kind of curious, like, why we would assume hydrostatic equilibrium modeling.
We don't have anything better, that's all.
Right, that's so crazy, right? Like,
No, we don't have anything better. That's the only answer. And then another thing is there that in the sun, we have done, there is a lot of radio observations and studies in the sun where people have looked at, we can do DEM analysis, like so, and you can get the density structures, density profile. And there has been cases where like people kind of overlay the radio contours on these and see like they are actually coming from plasma and so on. So you can get a rough density profile for active sun, quiet sun, solar, like sunspot. This has been done. And plain parallel atmosphere is pretty good assumption there.
Yeah.
So that's also why I choose that.
You said the type of sun blast from loops, right?
Hmm.
You can go up to the type of sun.
Mhm.
Can you distinguish, type of source can be a CME plasma or.
Yes,
different-
yes.
is it
We-
possible?
Yes, because
In the case itself.
yes, because if like I mentioned, so this is band limited because it's basically coming from the accelerated electron beams which are trapped in these arcades, but they do also go up, right? They can be in the plasmoids, and in those cases you see this band, the same band, because it's also having a height scale, right? The plasmoid structure, and this is moving, so you will have the drifting band there, and that's called moving type 4. That's even more rare. And yeah, that was in Proxima, they had a potential moving type 4. That's what, yeah. But yeah, nothing was seen in a very active star, so that's
Great. Some question. I work in the visible, right? My wavelength is my wavelength. The line is the best. And here you look and you know if it is a type 3 or a type 2 or a type 4 just on how they appear.
yes, that is from the. Yes, that's why we use the dynamic spectrum. So these type 3s also have drift actually, but they are so fast that you see it as a line. If you actually in high cadence spectroscopy, spectrographs, there are such milliseconds cadence and all, you can see even drift here, and people have estimated the speeds and shown that these are like C/3 roughly. And if you look at the X-ray observations, you can also estimate the energies, right, in KeVs. Just convert it into velocities, you probably get C/3. So it's the same electron beams. Yes. Yeah.
On your slide about where you detected the type 4 radio bursts in APVO, you mentioned that the solar model of the active region didn't fit, and you had to use this model too.
Yeah.
You said it was like significantly different than solar active regions. Could you say like a little bit how, like what's different about it?
I don't know. We can just say that, first of all, why did I even put solar active region is a big question, right? I mean, it's a completely different star, but that's the only known active region structure we have.
Right.
So only thing we can say is that that's not able to give you this kind of a nu P by nu B profile in the corona, so that you can observe these emissions at 750 megahertz, which you have here, So what it is, we don't know. Right. So we can say that it's not like the typical solar active region model, which actually I use the Ashwanden model, which he had for the loop structures. It flies quite often. Yes. Yeah.
it is possible they have thermal.
Thermal.
No.
Yeah, X-ray emissions people have seen, and yeah. And we actually wanted to do, we had actually multi-wave and approved for this observation where it would have been like we could get the energies, but it didn't trigger at the same time. So that's why, yeah, that's where we have to collaborate, radio and others. Yes. So then we can actually get like, okay, and if we have spectral lines, we can see the Doppler shifts, then we know something is actually flowing, right? Even if you don't have a drifting step. Yeah.
I have a dumb question that I think is kind of outside of your area of expertise. So I'm an interiors person and a fluids person mostly, and so the question is about why when you have at the very beginning of your presentation, when you have the two different branches,
Mhm.
why you get kind of an activity saturation with rotation rate. Do you have any thoughts about that? I'm curious about the different branches.
Oh, why
Like,
there are those? Oh, that's basically dynamo related, I would say. I mean, yeah, so one has a, the Rossby numbers are quite different if you want to think about that. So it's like very, yeah. So they have very high rotations, right? The rotation. So also they have their alpha omega dynamo. We don't know what the exact dynamo is. It's mostly omega dominated. So it has very high magnetic like dynamo activity there, and which is also why they have this strong dipolar shielding fields. Yeah. So yeah, we still don't know how the small scale fields are because we don't have observations. Zeeman Doppler imaging can go only till L equal to 4. And everything below is speculation. Yeah, it's science fiction below that. Yeah, thanks.